All right, AP Chemistry students, we are going to do a quick little video focusing on percent yield. And really this is just one extra step added on to our stoichiometry calculations and at times our limiting reactant calculations. So for this, the goal here is eventually to get to what is the percent yield. So in this question, because it's not always going to be broken up into these two parts, this is saying that we're starting with 34.5 grams of our potassium carbonate. And then it's going to be looking at, well, in the lab, we isolate 2.3 grams of water. What's the percent yield? So we're going to be analyzing just the water. We're not worrying about the other reactants or products. Now, this is important. Here, it's only giving you one reactant. If it gave you both reactants, so it also gave you, say, a mass of HCl, you would then have to think of this as a limiting reactant question. Because there's only one mass given for one reactant, we can go ahead with our calculation based on that one reactant. That's where the whole excess comes in for the other reactant. It basically means there's as much there that needs to be there to react, so we don't have to worry about how it affects our amount of product. So for theoretical yield, this is just going to be a stoichiometry calculation going from our 34.5 grams of potassium carbonate to the water. And again, that water I'm picking out specifically because it's asking for the theoretical yield of water, and that's what we isolated when the reaction was performed. So I'm just simply going to start with my 34.5 grams of K2CO3. Okay, I'm going to want to get to moles of it so I can go to moles of water. So using the molar mass, again, this is based on the AP reference tables. This would be 138.21 grams. That's equivalent to 1 mole of K2CO3. Here I'm going to use my mole to mole ratio. So for every 1 mole, and this is just from my coefficients up in the equation. So for my 1 mole of K2CO3 or potassium carbonate, I'm going to get 1 mole of water. Even though it's 1-to-1, please make sure you always show this. You can't just like skip that step and go from K2CO3 to water. All right, and then when we do molar mass, remember to always set that to 1 mole. So for 1 mole of water, you have 18.02 grams of water. Okay, so again, I'm starting with my reactant mass. It's the only one given, so that's going to determine our product, and then going to the product that I'm interested in. When you plug that in and going to the 3 sig figs that you started with, you're going to get 4.50 grams of H2O. And just like I mentioned in the limiting reagent question, the mass you get from the calculation is always your theoretical yield. Okay, this is just based on the math. It doesn't take into account what the chemist is actually doing in the lab. So this, again, from the calculation is always your theoretical. So getting to part B, if you start with this 34.5 grams of our potassium carbonate and you isolate 2.3 grams of water, and this is in the lab, you isolate this 2.3 grams, what's your percent yield? This mass would be your actual mass that you get in the lab setting. Okay, so using this formula up top here, and this is not the same thing as percent error, which we'll sometimes do in a lab calculation. Percent yield is very specific, where it's going to be for our percent yield, actual yield over your theoretical yield times 100. So from there, I'm going to have my 2.3 grams that I actually isolated from this procedure, and then I'm going to divide it by the 4.50 grams that theoretically I should have made just based off of my math, times 100. Make sure you always show that times 100. When you plug that in and with percentages, like we've done before, I always just write them to the 100th. We don't look at precision with the percentage, and then you'll have your percent sign. Okay, so even though I was only able to isolate 51.11% of what I theoretically should have made. Okay, so again, this percent yield calculation really is just an extension, one extra step from what we've been doing so far. If you look at kind of the one other type of question, which for you guys will look like this. All right, so for this next question, it's a little bit different, so I'm going to go through it with you because we're kind of working backwards than the previous question. So in this one, it says we have a research supervisor. He tells a chemist that they need to make 100 grams of this chlorobenzene and to expect a yield no higher than 65%. So how much of the reactant, in this case benzene, do I need to start with to make that 100 grams of the chlorobenzene if, however much I start with, I'm only going to produce 65% of what I make? So with this question, we're going to start with the percent yields. And the idea is we need to know theoretically how much would we need to make based off of this 65%. So I would go ahead and actually write out the formula just so you can see where everything is going. And remember, percent yield is actual yield over theoretical yield times 100. I'm going to plug in my 65 and I'm going to divide it by this 100 here so that I can have my 0.65. That 100 is what I actually need from the experiment. So that 100 is going to go in the actual value. Okay, and then I would have my theoretical yield, or this would be X down here. So then when you go to solve for X, sorry, I just wrote it both ways. When you go to solve for this, and I'm going to use, in this case, the 4 sig figs in this mass that I'm giving. Because again, percentages, I don't really look at it in terms of precision. So this is going to end up being then 100. If you go to do this, will be divided by 0.65. Okay, and again, I'm going to go to how I have my grams here. So this would be 153.8 grams. So what does that mean? I need to theoretically work to produce this 153.8, because if I can get a starting amount of my reactant that will theoretically produce this, a 65% yield will help me get 100 grams of it actually in the lab. So in this case, we're going to then start our stoichiometry with that mass. So this is 153.8 grams. This is based on this chlorobenzene. So this is my C6H5Cl. Then from there, it's just going to be using our stoichiometry. So I'm going to have my molar mass, which is 112.55 grams. And that's 1 mole of my C6H5Cl, so my chlorobenzene. Okay, I'm working backwards here. So for every 1 mole of chlorobenzene, okay, I'm going to need a mole of benzene to start with. And the last part is I need grams of it. So use the molar mass, which its molar mass is 78.11 grams of that C6H6. Okay, then when you go ahead and plug that in, 153.8 divided by the 112.5, 8.11. Okay, you're going to get this value here, rounding to the 4 sig figs that I started with. I'm going to have 106.7 grams of C6H6. So what that tells us is if the chemist starts with 106.7 grams of the benzene, okay, theoretically, he can produce 153.8. But what that means is because there's only a 65% yield from that, this starting mass of benzene will be able to get me that 100 grams of my chlorobenzene that I need. Okay, so a little bit more complicated. Just recognize when you're given percent yield, you want to think about how can you use that equation to start the calculation and then do stoichiometry afterwards. All right, you are all set.